Math 230, Cuesta College. I'm Joe Vasta, and we are going to cover section 6.5, counting notation. So we're going to start off this section with this little picture, but before we do that, I've got two puzzles that we will see the answers at the end. What comes next? So we have this symbol, that symbol, that symbol, that symbol. And then you have to pick which symbol comes next. And then this one right here, what goes in the box? Okay, so some number goes in there. So those are the puzzles. We'll come back at the end and do those puzzles. For this, we have Al, Betty, Carl, and Diana arrive at a movie theater. Here's the movie theater. How many ways could you line them up? And so, there they are. Let's figure this out. A way we can figure this out is by putting four slots. And you can say, well, if it was your job to line these people up at the movie theater, and they were like standing in a group over here, you would have four choices for that first spot in line. Okay, so maybe you put Carl there, I don't know. And then you would have three people over there, so then you would have three choices for that spot in line. And then there would only be two people left, and then you would have two choices for that spot, and then by default there's only one choice for the last spot. So how many ways can you line them up? Well, you'd multiply these together. This is the product rule for counting. 4 times 3 times 2 times 1, that gives us 24. So there's the answer there. But what we want to do in this section is introduce some notation for this, because this comes up a lot. What this is that right there. It's a 4 and an exclamation point. We don't yell out 4! That's not what we do. This is called a factorial. So what this means is 4 times 3 times 2 times 1, which is exactly what we have up there. And this is called 4 factorial. 4 factorial. So that's what it is. 3 factorial, and so 4 factorial, what you do is you just multiply till you get down to 1. 3 factorial, it's the same thing. It is 3 times 2 times 1, which happens to be 6. That's 3 factorial. And 3 factorial would be if you were just going to line up Al, Betty, Carl, and Diana wasn't there. So there's just 3 people. And there are 6 ways of doing that. Now I'll go through all 6 of those ways. You can go Al, Betty, Carl, Al, Carl, Betty, Betty, Al, Carl, Betty, Carl, Al, and Carl, Al, Betty, Carl, Betty, Al. So those were the 6 ways of doing that. Hopefully I said that correctly. Let's drop it down 1 here and go to 2 factorial. Well, 2 factorial is just 2 times 1, which is 2. So that's if just 2 people came, Al and Betty. And the 2 ways of doing that, the first way would be Al, Betty, and the second way would be Betty, Al. Now, some of you may argue when you write out these factorials, you really don't need to put the ones there, but you would be just ruining all the fun. Okay, so I'm always going to put the ones there, but you can argue you can stop at the 2, because the 1's not going to matter. Okay, the next one that we want to do is 1 factorial, which is just 1. And so that tells you how many ways you can line up just one person, which is Al, and I'll tell you that way. The one way is you put Al there. So there it is, 1 factorial. We're actually going to go down one more and say 0 factorial. And we're coming to the end of the paper here. 0 factorial, now if you've never studied this, you would probably want to say that that's going to equal 0. Now that, that's kind of a smart guess. But suppose it is your job to line people up. And that's all your job is. You line people up when they come. And nobody comes. How many ways can you do your job? 1 way, which is you don't do anything. Now, some of you might go, well, I don't like what you just did. 0 factorial equals 1. Well, if you don't like that, lots of books will say this is just a definition. So 0 factorial, we'll just say it's a definition, 0 factorial equals 1. But if that made sense to you, if no people come, then there's one way to line up those no people, which is by not lining them up. Then maybe that made sense to some of you. Okay, well, before we move on to some problems, let's go ahead and write up, let's see, I have 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial. Let's see what 5 factorial is. 5 factorial, and we'll continue it over here now. 5 factorial is 5 times 4 times 3 times 2 times 1. So you could say 5 times 4 is 20, 20 times 3 is 60, 60 times 2 is 120. Now there was actually probably an easier way of doing 5 factorial. 5 factorial, look at this. Here's 4 factorial. Look at that. 5 factorial is just 5 times 4 factorial. So you could have just said, what is 4 factorial? It was 24, and then go 5 times that, which gives you 120. Let's move on. 6 factorial. Well, that's 6, 5, 4, 3, 2, 1. Or we could just take this last one, which is 120, that's the 5 factorial, and multiply it by 6. And when you do that, you get 720. So factorials grow pretty quickly. You blink your eyes and they're grown-ups, and you're like, whoa, what happened? So look at this, 7 factorial. I'm not going to go ahead and write out 7, 6, 5, 4, 3, 2, 1. But that happens to be 5,040. 8 factorial is 40,320. Now here's something that you might not like, but a lot of us will not even live 8 factorial days. 8 factorial days is approximately, you can do this unit conversion on your own if you want, 110 years. Woo! So factorials do get pretty big. 9 factorial happens to be, you're just really multiplying 8 factorial by 9. That's going to be 362,000 880. So factorials grow fast, but we want to know this notation because we are going to be using this notation to solve some problems. So you might get something like this in your homework where they ask the following. So let's get rid of this. So in your homework they might say, here's an example. What is 5 factorial divided by 2 factorial? Okay, so we have to figure out what this is. This is going to help us with some things later on. 5 factorial is 5, 4, 3, 2, 1, and 2 factorial is 2, 1. So what we can do is we can cancel the 2's. And when we cancel the 2's, we say cancel, but we're dividing out. So those just become 1's there. I mean, you can put red marks to the 1's and put 1's above it, but that's kind of weird. So we don't have to do that. So look what we have here. We just have 1's on the bottom. We have 5 times 4 times 3. So 5 times 4 is 20. Times 3 is 60. Okay, so there's homework problems that help you practice your factorials. Oh, why don't we just do another one here? Like 2 factorial times 4 factorial. So some of you might be inclined to say, oh, well, isn't that going to be, you multiply and that's 8 factorial? And the answer is no. The order of operations say you do your factorials first. So 2 factorial is 2 times 1, which is 2. So that's this one right here. And 4 factorial, well, that's 4 times 3 times 2 times 1. And that was our original movie theater problem, and that was 24. So that's what you do. You do your factorials first, and then you multiply. So look what we have. We have 24 times 2, which is 48. And that gives us the answer. So now it is time to talk about ice cream. The No Rep Ice Cream Shop. They have 4 flavors: chocolate, vanilla, strawberry, and mint chocolate chip. Okay, so they only have 4 flavors. Doesn't look like they'll stay in business, but this is just for the sake of this problem. When you come to this ice cream shop, they're called the No Rep Ice Cream Shop. No repetition of flavors is allowed at the shop. So if you say, hey, I want a double chocolate, they'll kick you right out. Okay? So, I mean, that will certainly put them out of business. But anyway, we have a No Rep Ice Cream Shop. We have these 2 questions. How many different triples can you order? Order matters. And then over here, order doesn't matter. Order doesn't matters. Nice. Okay, so order matters, order doesn't matters. No one will even know there was an S there. Order doesn't matter there. Great. Okay, so how many different triples can you order? The first question is where order matters, and the second question is where order does not matter. Now, when you start doing this, the only way we can consider some of these problems is we can say, oh, look at this. We can have chocolate, vanilla, strawberry, and then here's your ice cream cone. There it is. And you can have chocolate, strawberry, vanilla. As you can see, it's going to take us a long time because I didn't even put the mint chocolate chip in any of these ones. It's going to take us a long time to list out all of our choices. The funny thing about this is order matters. So yeah, for some of you, it does matter. If chocolate is on the top and strawberry is on the bottom, and the vanilla is in the middle, I mean, this is completely different for some of you. So some of you say, you know, an order does matter when I get ice cream, and other people say, oh, well, it just all goes to the same place, and so this is the same as this. So that's what question 2 addresses, you know, where this is going to be the same as this. Now, because in your homework, I'm not going to have you list out all the possibilities, I went ahead and drew some pretty pictures of the possibilities. So this is included in the PDF. And here it is. Look at this chocolate, vanilla, strawberry, chocolate, strawberry, vanilla, etc. So here they all are. Look at that. And so when I have this up, this is just using chocolate, vanilla, strawberry for each of these things. And so when I do that, I've exhausted all my sources after doing 6 possibilities. There's nothing else that we can put in this rectangle that has strawberry, vanilla, chocolate without repeating one of these things. And then I went ahead and I took the strawberry out of the mix and put the mint chocolate chip in the mix, and then I went ahead and did this. And then I used chocolate, strawberry, mint for this, and then vanilla, strawberry, mint. And you can look at this and see that I have all the possibilities. And if you count them 1, 2, 3, 4, 5, 6, you know, you can go 6 times 4. However you want to count them, you see that the answer where order matters happens to be 24. Now we look back up here and we see where order doesn't matter, which means this is the same as 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 this. Which means chocolate, vanilla, strawberry, it could be in any order. This counts as 1. So 1, 2, 3, 4. So for possibilities where order doesn't matter, it is 4. Okay, so let's get a little bit more into this. Where order matters, that is called a permutation. When order doesn't matter, that is called combination. So we have these permutations and combinations. There are 24 permutations. There they are. And there are 4 combinations. So let's continue with this. When we have these permutations, so we'll move this out of the way, we could have done this problem the following when we do permutations. We could have, and maybe some of you thought of this, you can take this ice cream cone and turn it to the side. So I'll actually put the scoops on there. Okay, so the way we could have got that 24 is we could have put 3 slots, 1 for each of the scoops, and said, okay, how many choices do we have for our bottom scoop? Well, there's 4 flavors, we have 4 choices. It's the no rep ice cream shop, so after using one of the choices for the bottom scoop, we have 3 for the middle scoop. Now we've exhausted 2 of our choices, and then we only have 2 for the top scoop. Look at this. 4 times 3 times 2, that's 12 times 2 is 24. Well, is there a quick way of doing that with combinations? And the answer is no. So we have to think a little bit more about how to do these problems. First of all, let's introduce some more notation. We use the letter P for permutations. I had 4 flavors to select from, and I was selecting 3 flavors. So we have that, P, 4, 3. That equals 24. What these guys here are, these are permutations, so I'll just shorten this perms without, so W/O is without reps. Are there permutations where reps are allowed? Yes. And that's a normal ice cream shop, and you would have 4 choices times 4 choices times 4 choices. So yes, we have that, but we are focusing on permutations without repetitions. So in a similar fashion, we can do the same thing for combinations. We use the letter C, 4, 3, and that's what this number is. This equals 4. So these happen to be combinations without repetitions. No reps allowed, and that's what we have. Now, you may have had a statistics class where they had other notations for these. So another notation for permutations, and you might see this like on a calculator, is 4, and then there's a P, and that's a subscript there, and then there's a 3 here. And same with the combinations. You would have a 4, C, 3. So there's 2 subscripts. I like the notation that I'm using here, not this blue notation. Now, if you've had a statistics class, there's another way of writing combinations, and it's like this. So some of you may have seen this, but if you haven't, just ignore this blue part here. Put a 4 and a 3 within parentheses. Okay, the next thing we want to cover with this is we're going to be seeing these a lot, and let's start off with the combinations where you have a C, 4, 3, and that denotes combinations without repetitions. How do we say this? Well, the way you say this is, and I'll put it in quotes, 4, choose 3. So that's how you say this, 4 choose 3. And so maybe you took statistics and you remembered this. It's like 4 choose 3. Now, how do we say this guy right here? Well, that baffled me when I took a combinatorics class and I asked the professor, and the professor said, well, these are permutations of 4 taken, you take 3 items or whatever. It was very wordy, and I'm like, but isn't there a nice word like we have for combinations? And he said no, and I asked another teacher and they said no as well. So for this class, because I'm going to be saying these quite often, this is only going to be for this class, I'm going to use the word pick for pick 3. So outside of this class, if you say this to somebody else who knows math and you say 4 pick 3, they will not know what you're talking about. So you might say, well, you're just making things up. Believe me, this is going to make communication a lot easier when I'm doing the lectures. So I'll say 4, pick 3. You'll know I'm talking about permutations, and what will help you remember that is pick starts with a P, and so does permutation. Choose starts with a C, and so does combination. So that's the vocabulary that we are going to be using for this. And we hit some application problems. I'll try not to use pick and choose when I'm trying to have you determine whether it's a permutation or a combination. I'll probably use the word select. But in the real world, sometimes they'll use pick for a combination and choose for a permutation when they're just describing the real life application. So in this class, we'll try not to get you too confused, but maybe I've already confused you. So we have permutations, combinations. What is our goal here? Our goal is to be given something like this, like 4, pick 3 or 4, choose 3, and we want to figure out what the answer is. And that's going to help us in future sections. Another thing that makes this confusing is you've probably heard the word combination in your life. And maybe that is because you've had a combination lock. And those combination locks, they say, here's your combination, 23, 15, 8. And you know that you have to do 23 first, then 15, then 8. And if you decided to do the 8 first and then 23 and the 15, it wouldn't work. So with a combination lock, guess what? Order matters. So that should make you kind of mad. It should not be called a combination lock. What should those locks be called? Permutation locks. Permutation lock because order matters. I normally wouldn't bring this up, but if I don't, people think about this. Certain students will think about this, and then they'll get these confused. And really, it's just that name, combination lock. It's not a proper name. We will call it permutation lock, because that describes it like it should be described. So let's go ahead and focus on permutations first, and then we'll do some combinations. So let's go ahead and see what we have here. Oh, before we do anything else, I want to write something down here, up here. Four pick 3 equals 4 choose 3. Is that true? The answer is no. 24 does not equal 4. Okay. So how can we fix this equation here? Well, what do you know about 4 and 24? There's a few ways of saying this, but if you take 24 and divide it by 6, you get 4. So a way of fixing this is saying 4 pick 3 over 6 equals 4 choose 3. Why am I showing you this? This is called foreshadowing. Okay, so we'll come back to this when we look at combinations. Let's look at permutations. So permutations without reps, without repetitions. And so what we have here, problem number 1, is the one we already did. 4, pick 3. And what did we do? 4, pick 3, we just said it was 24, didn't we? But we also did this and we said it's like 4, 3, 2. So let me write that down. 4, 3, 2, which gives us the answer of 24. So our first method of cranking out permutations, when you're just given this, is called the countdown method, which will work most of the time. Okay, so the countdown method says you're going to be doing a countdown in your head or writing it down. The countdown begins at 4. How many numbers are going to be in your countdown? 3 numbers. So right here I'll say countdown begins at 4, and then this right here is countdown has 3 numbers. If you remember that, these should be pretty simple. Let's go ahead and do a problem that we don't know the answer to. So here's problem number 2. Problem number 2, we have this right here. So how are we going to say it for this class? We're going to say 8, pick 3. So where does our countdown begin? It begins at 8. How many numbers are going to be in our countdown? 3 numbers. So this is going to say 8, 7, 6, and we stop right there. So 8 times 7 is 56, and I'm doing everything without a calculator. 56 times 6, 36, 33, so 336. So 336 permutations. So if you went to this no rep ice cream shop and they had 8 flavors instead of 4, and you were going to get a triple, there would be 336 ways of doing that. And remember, permutation, order matters. These are permutations without reps. Now there is a formula that I'm going to put down in purple. For those of you doing the bare minimum, just ignore this. So I hope the purple shows up as purple in the video, but oh well. Formula. So some of you are just going to tune out of this because it's going to look a little more abstract. So you'll see this if you look in a counting book or a combinatorics book. We have n pick r. See, already people are like, okay, you've lost me. The formula for this would be n minus 1, n minus 2, ... We don't know how many numbers are going to be in the countdown. I mean, we know that there's going to be r of them. So r, and then these numbers, when you multiply them together, they're sometimes called factors. So there's r factors. Okay, so there's the formula. I put it in purple there. You don't need to memorize that formula. Just know how to do these kinds of problems. Why don't we go ahead and do another problem? I'm going to go ahead and do problem number 3. Ten, pick 2. So maybe you'll pause the video and do this one on your own, and maybe you won't. My countdown begins at 10. 10, 9. 2 numbers in the countdown, so I stop right there. So the answer is 90. Okay, so what I'm going to do is I'm going to show you another formula. And some of you are like, oh goody. So we'll make it in purple. We'll move this up like this. So let's call this one, let's label this formula, technical label here, another formula. Now there is a reason I'm showing you this one that's called another formula, because it's going to help us with 2 things. And after it helps us with those 2 things, we can just ignore, we can forget about this formula. N pick R. Now math people aren't too crazy about formulas that have ... So that may have upset some of you people. I'm not trying to insult you, but that may have upset some of you that there was a ... there. And so what math people try to do is they try to get a closed formula, one that does not have a ... That just looks so unprofessional. So what does that formula look like? I'll show you. It looks like this. N factorial over N minus R factorial. Do you see any ... And some of you are like, I see a dot there and I see a dot. That does not count. We don't have a ... like that. This is the professional formula for permutations without repetitions. Now what I'm going to do, I'm going to continue to waste your time with this problem. And some of you are like, you waste my time with this whole class. Correct. That hurts, but it's correct. I mean, it's math. What are you going to do with this in the real world? Except if you went to visit an ice cream shop, then you can use this. We're going to go ahead and do this problem using this formula, and I'll continue to use purple. Pick 2. Now, would I recommend this? No. Do the countdown method. But I'm going to use the formula to show you something. N, in my example, is 10. So I have 10 factorial. And then on the bottom, I have 10 minus 2. Of course, that's a factorial. Now, parentheses have the highest power, in terms of orders of operation. So I didn't mean to use the word power there, but okay, but they're the highest on the pecking order. So 10 minus 2, I simplify that to 8 inside the parentheses. So this is 10 factorial, and on the bottom you have 8, and then there's a factorial. Now I've got to simplify this. Now watch this. The top is 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and the bottom is 8, 7, 6, 5, 4, 3, 2, 1. Now we can write all that, but watch this little trick. 10, 9. Now, if it were my last day on the job, and my job was the countdown guy for NASA, I would completely mess them up and do this, what I'm about to do. Instead of going 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, I would go 10, 9, 8 factorial, and then I'd walk away. Say, see ya. Make sure you mail me my paycheck. That is really 10 factorial there. Now, why did I do that? Because what do I see on the bottom? At 8 factorial. What can you do with those 8 factorials? You can cancel them. And really, what do you have? You have 10 times 9, which is exactly our first step on the countdown method. That's why I would recommend the countdown method over this, but there's a reason I'm showing you this formula. First, this part right here is to verify, yeah, the formula does give us what we got when we did countdown. So 10 times 9 is 90. Okay, so there it is. So there are two places that I'm going to use this formula to get me something like a shortcut. So once I use this formula, not counting this here, but once I use this formula 2 times, we don't even have to talk about this purple formula anymore. So that is the deal. So I did this to show you it, but also to get us some things, okay? Let's go ahead and do problem number 4. Problem number 4 says this right here. 7 pick 3. I'm not going to use the formula. I want you to see if you can do this. Pause the video and see if you can figure out that permutation. 7 pick 3. So my countdown starts at 7, and it has 3 numbers in the countdown. 6, 5. 6 times 5 is 30, and then 30 times 7, looks like it's 210. So there it is. Let's go ahead and do another problem. Problem number 5. 5 pick 5. Countdown starts at 5 and it has 5 numbers in it. 5, 4, 3, 2, 1. 5 times 4 is 20. 20 times 3 is 60. 60 times 2 is 120. 120 times 1 is 120. Okay, so before we move on, 5 pick 5, what does this look like? This right here is 5 factorial. This would be if you walked into the no rep ice cream shop. They had 5 flavors and you wanted to get 5 scoops on a cone, no reps. There'd be 120 ways of doing that. But suppose this problem said 4 pick 4. Well, it would be 4, 3, 2, 1. It would be 4 factorial. And 20 pick 20 would be 20 factorial. So in a combinatorics book, and combinatorics is a branch of math that does study this, it studies other things as well, they would have a formula, I'll put it in blue, which would say n pick n equals, maybe you know what that formula would be. N pick n equals n factorial. Now, is that a formula to memorize? Absolutely not. I'm just having a math nerd moment, and if you watch the whole thing, watch the whole video up to now, I just tricked you into a math nerd moment. So n pick n is n factorial. Okay, that's very interesting. Now let's go ahead and do problem number 6, and this is the problem where some of you might freak out on. 5 pick 0. So 5 pick 0, the countdown starts at 5 and there's 0 numbers in the countdown, so what do we even write? That is a bit confusing. So what I'm going to do is I'm going to use the thing that is labeled another formula and put the 5 and the 0 into that formula here. So on the top we have 5 factorial, and on the bottom we have 5 minus 0. factorial? Well, 5 minus 0 is 5, so I have 5 factorial on the bottom. I also have that 5 factorial on the top. I could write that all out, but anything over itself is just 1. I mean, those guys are going to cancel with each other. And I end up getting 1 as the answer. So you might be thinking, wait, Joe, I thought we didn't have to use this formula in our homework. You don't, because I'm going to show you something that we could do instead. What if this said 7 pick 0? Well, 7 pick 0 would be using this formula, 7 factorial over 7 factorial, which is 1. And 20 pick 0 is 1. So instead of using this purple formula, which is not pretty to look at, we can just remember this. N pick 0 is 1. Let me put a box around this because this is something important to remember there. And it actually goes well with our ice cream example. You walk into the no rep ice cream shop. They have 5 flavors. And you order what? Nothing. How many ways can you walk into an ice cream shop, look at all the stuff, and then leave without getting anything? One way. This almost looks like it says, no. No ice cream for you, and there's one way that that can happen. So one way. So the next time, like, suppose we get, you know, if we had to do this problem again, like, okay, so P, we already know the answer, but 5 pick 0, we could just remember, oh, there's a 0 there. The answer is 1. So those are the permutations without reps that we just have to remember the answer is 1. Any other number that goes there, you know, like a 1 or a 2 or a 3, then we do countdown. So I'm always going to do countdown unless I have a 0 for the second number in this permutation. Now, other things to consider is that the first number will never be less than the second number. So you'll never have like 4 pick 7. You'll never have that. So you'll always be able to do the countdown. These numbers are always going to be positive numbers or non-negative numbers. There could be a 0 there. And permutation should just be something you practice in your homework. Now let's go ahead and look at combinations. So combinations without reps. The first problem we're going to do is 4, choose 3. Now we know what the answer is. Where is this sheet? 4, choose 3. We saw that it was 4. Now how did we get that answer? Oh, here it is. We had them all written out for us. And we said 1, 2, 3, 4. So order doesn't matter. But we're not always going to want to write them all out. But we also have this up here. 4, choose 3. Is what? Okay, so now the paper, both papers are moving here. 4, choose 3 is 4, pick 3 over 6. Okay, we're going to keep going on this. 6. Does this guy ring a bell? You're like, no, it's just the number 6. Do we see the number 6 anywhere here? Oh yeah, we do right here. 6 is 3 factorial. So this is 4 pick 3 over 3 factorial. So what is 4 pick 3? 4 pick 3 is 4, 3, 2. Countdown starts at 4 and there's 3 numbers in the countdown. And what is 3 factorial? Well, 3 factorial is 3, 2, 1. Does anything cancel? Yeah, the 3's cancel. There's 1's there. And the 2's cancel. There's 1's there. So it looks like my answer is 4. So 4 choose 3 is 4. We were able to get that putting the permutations over 3 factorial. Now, why did that work? And some of you might say, I don't care. But look at this. So 4 pick 3 happened to be 24. But remember what we did. So these are actually called equivalence classes. Maybe I shouldn't really be getting into that jargon. But look at this. Doesn't this remind you of, let me turn it this way. Just look at this one right here. Doesn't this remind you, here's the theater. And this is Al, Betty, Carl. And then we have Betty, Al, Carl. Remember how many ways could you line 3 people up at the movie theater? Well, it was 3 factorial, and there it is. So when you divide out by 3 factorial, then you are dividing out by 6, which gives you the 4 equivalence classes. And so that will always work. Why don't we try another example where we do not know the answer to? This will be example number 2. So the pattern maybe is this. You write the permutation that looks like that. And on the bottom you put a factorial, and that number that is the factorial is the second number. So watch this. 8 choose 3 is 8 pick 3 divided by, and then that number factorial, so 3 factorial. So let's see if we can do this problem. 8 pick 3 happens to be 8, 7, 6. And then 3 factorial is 3, 2, 1. Well, this right here is a 6, isn't it? So those cancel with that 6. 8 times 7 is 56. So the formula for combinations, and maybe we should have written that right away, was this. Some of you probably won't like this, what I'm going to write. N choose R is N pick R all over R factorial. So that formula does not have dot dot dots. We're pretty happy with that formula. There are going to be problems using that formula when both N and R happen to be bigger numbers. Okay, so you'll see. So there's really a better formula for combinations. And that's what I'm going to do. I'm going to go ahead and use that formula that we have. Where is it? Here it is. Where we said another formula. And I'm going to redo this problem. And by redoing this problem, I'm going to come up with the better formula. Okay, so there's a better formula than that. Okay, so but I have to use this thing labeled another formula. So if you're confused, I don't know what to say. We'll see the pattern, and then when we hit number 3, we can use the better formula. But I'm deriving the better formula through this example here. Eight choose 3 is 8 pick 3 divided by 3 factorial. Now, using that thing labeled another formula, 8 pick 3 becomes 8 factorial over 8 minus 3. What is 8 minus 3? Well, that would be 5. And then we have to put a factorial. This right here became this. Am I going to get the same answer, 56? Yeah, I'm going to. And then you also have the 3 factorial on the bottom. Now that 3 factorial on the bottom is actually over 1. And you may have remembered in an algebra class that if you are taking a fraction and dividing by another fraction, there's something called copy dot flip, invert and multiply. So I'm going to do copy dot flip. Copy the top. Dot, that's multiply, and then flip the bottom. 1 over 3 factorial. So that is what I have there. And what I'm going to do is, I think I'll write the bottom, it's just multiplied. I'll write it in a different order. This thing gave me 8 factorial on the top, and on the bottom we have 3 factorial, so I'm writing that one first. 5 factorial. Now, I should be able to finish this problem, but that's not the important part. I mean, we know we're going to get 56, and maybe I'll verify that after I say a few things. But look at this formula for combinations. This is the better formula. Look, you've got an 8, choose 3. The bigger one, which is the first one, went on the top as an 8 factorial. The smaller one, which is the 3, went on the bottom as a 3 factorial. And then you put another one on the bottom where those guys will add up to the top. Or this 5 right here is really just 8 minus 3. This formula that I described, I'll write out in blue and I'll put a box around it. N choose R is n factorial. See, that's what I had. I had the 8 factorial. And then I have 3 factorial, so this is r factorial. And then this 5 is really the 8 minus 3, so we'll go n minus r. That's a weird looking r, factorial. And that right there, let me go ahead and box it here in a bold color. That is the formula, and you might see that in a statistics class. That is the formula for combinations without repetitions. This will always give you your combinations. And so we used this thing called another formula. In this case, it was 2 strikes, you're out. We're done using this thing called another formula. We don't need to use it again. And the formula that we'll be using is this one right here. Now, does this give me 56? Some of you do care about that. Well, let's see. 8 factorial is 8, 7, 6, 5, 4, 3, 2, 1. But what I'm going to do is I'm going to make it go down to 5 factorial. 8, 7, 6, 5 factorial. And then you have the 5 factorial on the bottom. And then you have 3 factorial, which is 6. I'll just write it as 6 this time. And look what happens. The 5 factorials cancel. And then look, 8, 7, 6. 8, 7, 6 times on the bottom there was a 6. And the 6's cancel, which gives you the answer. 8 times 7, 56. So this is a nice formula that will work. And this is really beneficial when these two numbers are closer to each other, I believe. could be saying that wrong, but I think I'm saying it right. I don't. Let's do another example. So the next example that we do is I need another piece of paper. Will be problem number 3. So here is problem 3. Ten, choose 8. So what we do is we use this formula. You put 10 factorial on the top, 8 factorial on the bottom, that's that R part, and then you want the bottom numbers to add up to 10, so you're going to need a 2 there, 2 factorial. Now we could have said 10 minus 8 is 2, so maybe I should have done that. Let's continue. 10 factorial is 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Now some of you really like that and you're going to write that out. But I'm lazy and I'm going to go all the way down to which one? The bigger one. So I'm going to say 10, 9, 8 factorial. There's the 8 factorial right there. On the bottom, we'll keep it just like that, and then this one here, we'll write it out. This is 2 times 1. You don't really need to write that 1 there. So look what happens. The 8 factorials cancel. Those become 1s. What else cancels? The 2 and the 10. And 10 over 2 is 5 over 1. So what does that give me for my answer then? On the bottom, there's just all 1s, and on the top, it's 5 times 9 times 1, which is 45. So even though this formula looks like, oh, we're always going to be doing fractions, you'll never get a fraction in the end. You'll always be able to reduce this, so there's all 1s on the bottom, and then you'll always get a nice number like 45. So once again, these are combinations without repetitions. If you went to the no rep ice cream shop and they had 10 flavors and you wanted to get 8 on a cone and you said, order doesn't matter, it's 45 ways of doing that. So we have the answer for problem number 3. It's our combination. Had we done it the other way, so I don't even know if I should do this. I'll do it in green, okay? So please, I mean, for most of you, for 98% of you, just fast forward the video till you see me write number 4 down. So suppose I did it like this and I said this is really 10 pick 8 all over 8 factorial, then you'd have 10, 9, 8, 7, 6, 5, 4, and there should be 8 numbers in that countdown. 1, 2, 3, 4, 5, 6, 7, and then it would be 3 here, and then you'd have 8 factorial, which would be, look, 8, 7, 6, 5, 4, 3, 2, 1. You'd have to do a lot of writing because those numbers, I mean, 10's kind of big and 8's next to it, and then you would have to cancel things out. You'd cancel the 8, 7, 6, 5, 4, 3, and you'd have 10 times 9 over 2 times 1, that's 90 over 2, which is 45. So it still gives you the same answer, but there's a lot more writing. And that's why we like this pretty formula here. And you're like, you called it pretty. Beauty's in the eye of the beholder. So let's go ahead and do problem number 4. Problem number 4. Maybe you want to pause the video and do this one on your own. This is 7 choose 3. So please use this formula here and see if you can do the problem. So we have on the top of the fraction 7 factorial, and on the bottom we have 3 factorial, and then 4 factorial. Okay, those guys have to add up to 7. And so 7 factorial is 7, 6, 5, 4, 3, 2, 1. But we're going to stop at the bigger one, which is 4. So this is 7, 6, 5, 4 factorial. On the bottom we have the 4 factorial there. And then 3 factorial is 3 times 2 times 1. The 4 factorials cancel. Those become 1s there. And then right here you have a 6. That's going to cancel with this 6, and those will become 1s as well. So you have all 1s on the bottom, and you have 7 times 5 on the top with some 1s, and then that gives me 35. So these problems, I mean, this formula actually does look worse than it really is. Let's go ahead and do a few more problems. Number 5. Number 5 is 5 choose 5. Okay, so let's go ahead and put this into the formula. We have 5 factorial on the top. That's this 5 here, not that 5. It's the first 5. Now the second 5 goes on the bottom. 5 factorial. I know you're saying, well, Joe, come on, what's the difference? They're both 5s. The difference comes to play when you have a problem like this. Now, what plus 5 gives me 5? Or you can go 5 minus 5. You have 0 factorial. That 0 factorial is 1. Remember the definition? So you just have 5 factorial over itself. Something over itself is just 1. Now I believe we did a problem earlier with permutations and it was 5 pick 5 and that was 120. How is it that 5 choose 5 is just a 1? Well, the formula gives it to us, but let's think about this physically. You go walk into the no rep ice cream shop, all they have is 5 flavors, and you say, I want all 5 of those flavors on a cone, or maybe you could actually make a big malt out of it, but let's just say on a cone, and order doesn't matter. How many ways can you do that? Just one way. You put a scoop of each of the 5 flavors on a cone, and order doesn't matter. That's why the answer is 1. Let's continue. Problem number, so the formula is going to go away. I mean, I'm just moving it out of range there. Here's problem 6. 5 choose 0. So what's on the top of the fraction? That 5. So we're going to go 5 factorial. And on the bottom we have 0 factorial. And then 5 minus 0 is 5. 5 factorial. So the bottom ones add up to the top one. That 0 factorial is 1. So you just had 5 factorial over 5 factorial, which is 1. So as I was doing on problem number 6, I thought, wow, that kind of reminded me of problem number 5. There's some symmetry going on. I'll come back to that statement after I do problem number 7. Problem number 7 is going to be our final problem for this section 6.5. Let's see what we have for this problem number 7. Is 50 choose 2. So that's quite big. I mean, the ice cream shop has 50 flavors. You're going to choose 2 of them. A double for a cone where order does not matter. So how many ways can that happen? Let's go ahead and put 50 factorial on the top of the fraction. We're using that formula. And then you put the small one on the bottom, 2 factorial. And then you want to go 50 minus 2, which is 48. 48 factorial. Now, I'm not going to verbally say 50 factorial because it goes all the way down to 1, but I'm going to just make it go down to 48 factorial. Watch this. 50, 49, 48 factorial. This is all over. You have the 48 factorial from here, and then you have 2 factorial, which is just 2 times 1. You don't have to write that 1. The 48 factorials cancel. The 2 and the 50, they will reduce to 25 over 1. So basically all you have here is 25 times 49. So I'm going to go ahead and do that multiplication right here. 5 times 9, 45. That's a 4 there. And then we have 20 plus 4. This is 24. And then over here we have 2 times 9 is 18. And we have 8, 9. So I add these. Maybe it's been ages since you saw someone multiply 2-digit numbers together. And we have 8 plus 4 is 12. Carry the 1. 9, 10, 11, 12. So the answer then happens to be 1,225. So there it is. So these are combinations without repetitions. There are combinations where reps are allowed, and there are permutations where reps are allowed. We may look at a combination where reps are allowed in a future lecture, but it won't be part of the homework. So let's take a look at something now. Remember back here where I said, hey, look, there's some symmetry. What have we done in this class that has symmetry? Well, something that we've done in this class that has symmetry is Pascal's triangle. So I'm going to show you another way of considering combinations. So let's take a look at this first one here. 4 choose 3 was 4. So Pascal's triangle says, hey, let's go to row 4, which is that one right there. Put your finger on that first one and you're going to slide over 3. 1, 2, 3. It's 4 right there. Next one. 8 choose 3 is 56. So which row do we go to on Pascal's triangle? We go to row 8, which is this right here. You don't want to count that as your first entry. That's entry 0, and you're going to move over 3. 1, 2, 3, 56. And there it is, 56. So you might be thinking, well, why this formula here? And you'll see. You'll see that there may be a time or two on the exam where you have to use this formula. Let's go ahead and look at problem number 3. 10 choose 8. So I need another color. I'll use purple here. 45. Go to row 10 and move over 8. 1, 2, 3, 4, 5, 6, 7, 8. 45. The next example. 7 choose 3. It's 35. Go to row 7 and move over 3. 1, 2, 3. 35. The next one, I guess I'll use red. 5 choose 5. So 5 choose 5, you go to row 5 and you move over 5. 1, 2, 3, 4, 5. And here's the symmetry that we were talking about. almost all out of colors here. I think I'll use this color right here. 5 choose 0 was 1. So you go to row 5, choose 0. That means you're not moving over. You end up getting 1. So there's symmetry in Pascal's triangle. There's symmetry in combinations. You can use Pascal's triangle to do lots of combinations. The only problem, and the reason I showed you the formula was because I was supposed to show you the formula, but also because of a problem like this. 50 choose 2. You would have to go to row 50 on Pascal's triangle, which would take a lot of work to fill out a Pascal's triangle that goes to row 50. This is row 10, and then move over 2. And so that's why we showed you the formula, because on ones that are bigger, and you won't get that many, you then would use the formula. So for lots of the combinations without repetitions, especially in the next few sections, I'll probably just be pulling out Pascal's triangle on the smaller ones. Now there is no triangle that will help you get permutations, but the permutations can be done using countdown unless the second coordinate is 0 and then the answer is 1. So there it is. We end up with Pascal's triangle. This is kind of where we started the class, sort of. I mean, not immediately, but when we saw that Pascal's triangle in one of the first few sections, who would have thought that it would come back and haunt us in this section? Now, let's go ahead and look at the answers to the puzzles. If I can find, here it is. Yeah, I've got both puzzles here. So what comes next? Now, if you kind of turn this to the side, or turn it, maybe to this side, you can see that this guy here reminds you of the letter K. L, M, there's an N. So what comes after N in the alphabet? O. The next puzzle. What goes in the box? Okay, well, some of you are not going to like this. How did we get 27 from these guys up here? And then why does this one just have, why is there just one line coming out of the 79? Okay, what you do is you add up these digits. So 8 plus 8, that's like 16, plus 6, 22, plus 5 is 27. Okay. How's this one gotten? Well, it's just 8 plus 8 because there's only one line going into it. And how's the 31 gotten? By adding up these digits. So let's see if this actually works. So this is 15 plus 9 is 24 plus 7 is 31. So how's this 9 gotten? Well, there's no line there, but we went 2 plus 7 is 9. And then 11 is 6 plus 3 plus 1 plus 1. So that's 11. So we add up these digits right here. 9 plus 1 plus 1 is 11. This concludes 6.5. Do your homework. Have a good day. I'll see you in the next video.